All right, in this last segment, we're just going to cover bass traps and resonance in enclosed spaces. So a bass trap is all about creating destructive interference. So destructive interference from before, all right, happens at odd half wavelengths. So you can do this at lambda over 2. You could do it at 3 lambda over 2, but that makes your bass trap much bigger. I'm not sure why you'd want to do that. So you can do it at lambda over 2. How do you get lambda over 2 out of a bass trap? Well, if you design something that's lambda over 4, the sound comes in for a quarter of a wavelength, bounces off, and goes back for a quarter of a wavelength. By the time it gets back out to here, it's been a half a wavelength. And so the reflected sound is canceling out the incoming sound. Right? So bass trap is designed so that the bass, the signal that you've designed it for goes in and doesn't come out. And around that signal, it has some effectiveness. Right? And we'll probably look at that. I'm probably going to have you do that in your lab piece, but we'll do it virtually with Excel. Right? So there you go. That's the essence of a bass trap. Now you'll find out there, and I'm going to put a paper I think on Canvas about a bass trap that has you know, one of the problems is these are deep, right? These are, I mean, these can be really big. Um, there's a French group that's done some work on using spirals to create planar bass traps. There are other groups that have worked on how good a bass trap do you have if you turn this into something that's curved so it's not as deep. There's all kinds of work going on bass traps. The other thing that people do with bass traps is, you just need the sound to go in and not come back out. And so what they'll do sometimes is they'll put some absorbent material down in here as well. So you're canceling out part of the sound with that. And so you attenuate the sound as it goes in and as it comes out. Your goal at the end is just to not have the sound reflected back out. Last but not least, when we talk about enclosed spaces, this is basically singing in the shower, right? I mean, everybody loves to sing in the shower. Your voice sounds so great because there are resonances all over the place. You've typically in an enclosed space, a closed space being any sort of smallish room. And if you have a bass voice, it's easier to hit these because you know um, the smaller spaces tend to be more on par with the wavelength we're talking about. Well, before a couple of weeks ago, 3 weeks ago, we talked about tubular instruments closed on both ends and that they resonate at half wavelengths. Yeah, and we're like, yeah, there really aren't any instruments like this. But there is when you're in an enclosed space, right? So you take any standard rectangular space, and you could think about the third dimension up and down as another dimension, which is always going to be about 3 meters or so. This If that is a multiple of half wavelengths, you're going to get a resonance in there. And the same here, multiple of half wavelengths, you're going to get a resonance. So one of the reasons your voice sounds the way it does in the shower is you're doing a good bit of this. And there are a lot of places where you can actually, if you pay attention, you can hear what the resonance frequency is of the space you're in. So we'll have some problems on this as well. All right, that's it for reflection interference, and look forward to seeing how you do on the problems.